Good old-fashioned AI.
All right, let's get started, folks. Good evening, and thank you all for coming to this talk. We have Jacob Andreas, who's a professor of computer science here at MIT and works on language models and language and understanding communication and a whole bunch of stuff. He has a number of accolades, which I'm not going to list here. You can visit his website to see those. But please welcome Jacob.
Thank you. So what this talk is going to be about is, I guess sort of specifically about solving decision-making problems by automatically constructing little symbolic models on the fly. And hopefully that'll be kind of an entry point into talking a little bit more generally about the role of symbolic computation in the modern machine learning landscape. I haven't looked at these slides in a little while, so I apologize if this is a little rough. So to start off here, let's imagine an AI researcher who is trying to build, maybe something that looks like a household robot who's trying to do these kinds of tasks in a kitchen that can, chill a bottle of wine for you and put it in the cabinet, that can heat up some food and put it on the table, and so on and so forth. And let's suppose that our researcher already has access to a robot platform that provides some basic affordances here, maybe some sort of simple perception and action capabilities. We have access to something like a structured state representation or scene representation that's already detecting all of our objects and telling us what properties they have, what relationships exist between those things, and maybe that we've already sort of equipped this system with what we might call like mid-level actions for doing things like moving around the world, doing pick and place, things like that. And let's suppose finally that the year is 1974 and that our robot looks something like this, and that our screens are all black and green and all that good stuff. What do we do? How are we going to build this system? And the high-level structure of a system that we might build in 1974, right, looks not so dissimilar from the way we might go about solving this problem today. We're going to have some little module that does language understanding. We're going to have some module that, basically translates the natural language command from a user into some sort of formal representation of a goal. We're going to have some system that turns that goal representation into a plan, and then we're going to send it off to the robot, and the robot's going to take actions. But when we think about how we actually go about implementing each of these steps, these look quite different maybe from the way that we might do this today, right? When we want to do the language understanding piece of this system, we're probably going to require our user to speak some controlled subset of a language, probably English. We're going to write some sort of symbolic grammar that knows how to parse this limited subset of English that we've instructed our user to produce. And what we're going to get at the end is maybe some sort of logical representation of the goal that the user is trying to accomplish here. When we think about how to do, or I guess the system builder, when we think about how we're going to do planning in this system, our system builder is probably going to do this symbolically as well. I don't even know how much they teach this stuff, especially at other schools in the undergraduate curriculum, but the way classical planning approaches work, right, is that you start by defining some set of high-level actions. In our kitchen domain, right, they might be things like slicing food items or transferring food from one plate to another. And you're going to write down for each of these actions its preconditions and its postconditions, right? The things that need to be true in order for you to even attempt to run this action, and then the things that are going to become true afterwards. And once you have a symbolic representation of a goal expressed as a set of these postconditions, once you have a set of actions with defined preconditions and postconditions, you can take your favorite search algorithm and try to find a sequence of actions that's going to be well-formed in the sense that every time I take an action, its preconditions are satisfied, and ultimately the postconditions that obtain are the ones that the user wanted to get and specified in natural language. How well does this system work when we try to actually run it in the world? Perception, control, maybe not so good, right? None of the kind of robustness we've come to expect from modern computer vision systems. We're probably going to be working in a blocks world, maybe a literal blocks world, maybe not even sort of instantiated in a physical environment, but on a computer. But within this world, right, we can actually handle some pretty remarkable forms of generalization in the space of possible user requests, right? The nice thing about both these symbolic language understanding methods and these symbolic planning methods is that if you've described your world correctly, right, if this sort of formal model that we built is actually the right formal model, and you have the compute power to sort of generate arbitrarily complicated plans, then you can generate arbitrarily complicated plans, right? Starting from maybe arbitrarily complicated goal specifications and initial states of the world. Now, I just said that the system can handle remarkable forms of generalization, but a natural question to ask here with our sort of maybe machine learning hats on here is generalization from what, right? No part of this process or this pipeline that I just described involves learning. This is a rule-based system that some person sat down and engineered, right? So to the extent that there's a learning algorithm at work here in building this system, it's one that lives in the head of the researcher, and the data for whatever learning algorithm she's running is just whatever set of examples that she thought about in the course of trying to build the system out, or maybe played with in the course of trying to debug things that were going wrong. Plus, whatever background knowledge she had about the world in general and about how sort of planning problems in general and kitchens in general work before trying to build this particular system. And the number of problem-specific examples that she had to think about in order to get a version of this working was probably on the order of like tens to hundreds. And so in that sense, the learning algorithm, right, that's building the system that we looked at here really is incredibly sample efficient, learning from very small numbers of examples. And I think in that sense, meaningful to talk then about generalization to these more complicated goals and more complicated plans, maybe than the system builder herself ever had to reason about in order to put this thing together in the first place. Another nice property of this system that we've built is that we understand quite well how it works. It's code. It's probably not that much code. A human being wrote it all down, and we can use it to prove things like the robot is never going to leave the refrigerator open, or if the environment contains a stove and a refrigerator and a knife, then we can guarantee that it's possible to satisfy every goal that the user wants to accomplish, things like that. On the other hand, if the examples that our researcher thought about here were data, then the learning algorithm that she had to apply to transform that data into a working model was kind of horrible, right? It probably took several years to build out the system. Maybe we give her a PhD at the end for her trouble. And in practice, a lot of this time was probably time spent thinking not about planning problems or sort of robotics in general, but like thinking about kitchens and trying to figure out exactly what objects and what states we need to keep track of, what high-level actions we need to implement for this planner, what the preconditions and the postconditions of those actions are, right? Do we need to keep track of doors in this environment and whether doors or opens are closed? Is being sliced a property of a potato, or does slicing turn a potato into a collection of sort of atomic objects that can each be manipulated individually? And this is going to be an issue because if the world changes, maybe even just like in very small ways, the system isn't going to work anymore. And the changes that we need to make sort of underlyingly might be non-trivial, right? If we do decide that suddenly we need to keep track of doors, we need a bunch of door manipulation operators, we need, sort of things that we can perceive that monitor the status of the openness or closedness of doors. The preconditions for all of my actions are going to change if those actions involve with objects containing doors or paths that go through rooms that have doors between them. Some of these conditions are themselves going to maybe require new sensors that we have to put on the robot, new low-level controllers. All of which is to say, right, that with, while the generalization of this system is great, the generalization of the approach that we took to building this system across problems and the work that we're going to have to do sort of marginally to spin the system up in some new problem domain or even a variant of this domain is maybe a little bit less appealing. Okay, so the year is 2024, not 1974, and some pieces of this story have changed substantially. Like we said before, we're going to need to do some amount of language understanding here, and now language understanding or aspects of language understanding are in some sense easy. We can get really high quality sentence representations, either from some pre-trained language model that we can use to judge sort of similarity of goals. We can maybe even translate directly into a formal goal representation if that's what we want, just with an off-the-shelf large language model that we can download without having to do any additional data collection or any work on our own, just by taking a big LM and prompting it to basically be a semantic parser. Our system needs perception, and now perception is pretty easy, right? We can get a big pre-trained vision model. We can just get it to sort of automatically segment the world into the categories of objects that I care about. If I change my mind about what those object categories are, I just like edit a text file somewhere, and now I can recognize a new set of objects, and I can classify these. I can classify all the relations between them that I might ever care to reason about. Our system needs the ability to do low-level control, right? All these sort of things that we said were going to be our pre-provided or maybe even mid-level operators, our pick and place, are moving around the environment. And if we're willing to go out and collect a gajillion demonstrations or spend a lot of time letting systems do kind of RL on their own, maybe even without a human in the loop, we're going to get reasonable low-level controllers. But this high-level planning step, right? Building systems that can sort of reason over very, very long time horizons and chain long sequences of these mid-level actions or high-level actions together, and especially systems that can learn to do these from super small numbers of examples, this is still a really hard problem. There's been a ton of interest in the last couple of years in sort of language-based planning, starting with some work by like Mohit Sridhar, by Pratyusha Sharma, who's sitting in this room right now. And you can use language models to do some amount of planning and to inject some amount of common sense reasoning into these sort of high-level planning problems, but they still really don't scale up to like very complex tasks, very complex environments with lots and lots and lots of these actions chained together. And in particular, they really don't give you the kind of generalization and the kind of robustness that the symbolic planning approaches that we were looking at on our sort of black and green slides did. And they certainly don't come with any of the kinds of formal guarantees that we got from those systems. We really have no idea what's going on inside these models or for what kinds of goals they're going to fail to generate viable plans. And so a lot of the sort of real world robot systems that can solve real hard planning problems that people are actually building still rely on some amount of manual definition of features and skills, and generalization at the task level, in some ways is still as painful as it was in the sort of first version of the system that we looked at here. And this is also some work from Tom Silver and folks at MIT. And one thing to point out here is that this is not just about robotics. This is not just about sequential decision making generally. Inside, sort of machine learning based approaches to theorem proving, to program synthesis, to inverse graphics, there is still a huge amount of human symbolic representation engineering and symbolic search, sort of making these systems actually work. And when we talk about the history of sort of AI today, I think there's a sort of popular narrative that the deep learning stuff won because symbolic systems just don't work. They just can't be made high recall enough to use for any practical application. And I think in some problem domains, this is clearly true, right? Good luck trying to write down some symbolic definition of a chair that will actually allow you to recognize every chair in every condition that a chair will occur for every object that a human being is willing to label as a chair or even a dog. But in many other domains, I think the actual lesson of the sort of deep learning revolution is a lot subtler. And it's that symbolic systems can be made to work. Sometimes they can be made to work even much better than these kind of big end-to-end representation learning approaches. But it's just not worth it to try to do that. That in building symbolic models or some, class of symbolic models of the kind that we've been looking at so far, the sort of human intellectual effort that's required to build out a system in a new domain scales linearly in the number of problems. Whereas with, sort of generic machine learning approaches, the incremental effort that you need to sort of apply these to a new problem domain is small enough that it might as well, we might as well think of this as a sort of constant scaling. And so these big learning-based approaches that we're showing on the bottom, maybe unlike classic symbolic system building, let us adapt quickly to changing goals, to a changing world. But as we said before, that's really going to come both at a cost in generalization, sort of within an individual problem domain, a cost in interpretability, a cost in robustness. And so what most of this talk today is going to be about is developing techniques for building symbolic systems or systems that exhibit all the nice properties of symbolic systems while maintaining sort of ML-like or deep learning-like scaling in the sense of trying to come up with some sort of general purpose technique that we can reuse across problem domains, not just individual problems. So we'd love to build some kind of box, right, that replaces our 1974 graduate student, maybe does her job for her much faster, that does the work of sort of building informative examples, figuring out how to represent them symbolically, and then integrating these symbolic representations into some kind of end-to-end system. The year being 2024, it's going to surprise nobody here that our solution is going to use some kind of large-scale language model pre-training. But I think it should have been clear, even back, sort of when we were thinking about how to build the original versions of these systems, that the long-term solution might need to involve something like this, something that involved something that looked like large-scale pre-training on a big text corpus or on a big sort of unstructured data distribution, right? After all, the data that our hypothetical grad student here is using to build out this system is both a set of individual examples that she's reasoning about in every domain, and like literally everything else that has ever happened to her in her life, every classroom she's ever been in, every textbook she's ever read. And if we think about where we might get access to that kind of knowledge for automated reasoning, a large part of that is going to be contained in language, in sort of books, in lectures, in papers, maybe even, the papers that this very person wrote. And so, at a high level, what we're trying to do here is just replace some of that or build the best substitutes that we can using the kinds of now sort of large models that we have lying around. Obviously, this is a sort of big grand vision, and we are not going to get all the way there today. We're not even going to get like close to all the way there today, but I think some interesting first steps. So in the rest of this talk, I'm going to present a couple of systems that sort of roughly implement this high-level vision that are using sort of big LMs to interactively build symbolic systems tailored to domains of interest to do things that we can't do with those LMs alone. The first of these is actually going to build off of our running example and look at sort of learning planning representations for sequential decision-making problems. And the second is going to be about program synthesis, about kind of interactively building libraries of code to support maybe even more general inverse problems. I think there's also a sort of general lesson here about how good symbolic systems are as some of the people think of as like fundamental challenges or maybe like, challenges that we can't get over in big LMs right now. And so if time permits, we'll end with a very brief discussion of how to use maybe some of the same ideas to actually make LMs themselves better. Cool. So let's dive right in. And the first project I'm going to be talking about here was led by MIT PhD students, Leah Wang, Jiayuan Mao, and Pratyusha Sharma. So how does our hypothetical graduate student on the first day of her project figure out how to build a good kitchen robot? I'm putting robot in scare quotes here. We are actually starting to work with some like BDAI spot type things to get these things onto real robots, but everything I'm going to show you today is in a very silly simulation called AI-Tutor. Okay, so how does our grad student do this? Well, maybe she starts to write down some examples of the kinds of commands we'd like users to be able to issue to this system, the kinds of commands that we'd like to be able to interpret. And maybe in the course of planning the system out, she also writes down some plans, maybe some high-level symbolic plans that might be associated with each of these natural language goals, expressed in terms of hypothetical high-level actions that maybe we don't even know how to implement right now. And maybe once we've written these things down, let's start to think about what these actions are. What's an action? It has a name, it has a precondition, it has maybe some preconditions and postconditions, all expressed in terms of things that we can sense in the environment, right? Assuming access to that sort of relatively low-level perception that we were talking about before. So if we forget about our plans for a minute, we might even just take a minute to write down what we think these preconditions and postconditions are for each of these steps that we put into, or each of these actions that we put into our kind of putative plans at the beginning. And we can do this, right, for our put action. We can do this for all of our other actions as well. And now that we have these, let's go back to our original goals that we were trying to sort of spec out and see if we can actually come up with plans that satisfy these goals. And maybe in the course of doing so, right, we discover some mistakes in our original plans, right? Here we said we were going to start by chilling the wine, but as we've implemented our high-level actions, we actually need the robot to be holding the wine first before it can chill it. And so maybe we need to go back and revise the plan so that it ensures that the robot is holding the wine. And, this is to be expected, right? We didn't even know what the definitions of these actions were going to be when we first wrote down these plans. We might need to do a little refinement at this stage. Okay, are we done? And not quite, in the sense that these actions, even though we've sort of formalized them symbolically right now, are still totally abstract. And we need some way of getting our robot to actually execute these plans by and maybe one possibility is for each of these to write down like a fixed sequence of low-level actions that we can guarantee will actually accomplish it. And maybe we can manually define a little controller using our sort of control theory hats. In our hypothetical example here, right, maybe our student discovers that chilling is more complicated than she realized. We can't figure out how to write down all of these low-level controllers by hand, starting from all possible starting configurations. And so maybe she even goes back to the drawing board, right, and comes up with, an even finer grained set of high-level actions that break some of our previous actions into pieces, such that each of these things is now a little bit easier to implement and offload some of the hard reasoning to our symbolic planner. And maybe some of these things we don't even want to try to define by hand, but we're going to come up with like now very simple isolated learning problems that we can collect a little bit of supervision for on its own. So what I've described so far is the sequence of abstract actions that a human might take to build some sort of symbolic controller. So what would it look like now to automate this process? And here's a sort of flow chart for what we just did, right? We start with some symbolic action representations. We stare at these and we try to figure out what sorts of plans they should correspond to. We'll use our ideas about plans to refine our symbolic action definitions and vice versa. And once we're satisfied with these, we'll take all of our plans and our symbolic action representations and use them to go out and actually implement some controllers that satisfy the symbolic definitions that we came up with at the beginning. Now, the first of these steps, right, generating our symbolic action representations, is really just about generating some code based on a high-level natural language description of what it is that we want this action to do. And this is the sort of thing that modern language models, or language models that have been, pre-trained, fine-tuned on some amount of code, are amazing at. So let's just do this with a language model, give a language model our natural language description of the action and ask it to write down in scripts or in the formal representation of our choosing a symbolic definition of this action. Okay, here are the bits of our system that look like planning. And once we have these symbolic action definitions over here, right, we can solve these things with, existing super mature, super robust planning tools. These planning tools, of course, also need symbolic goals for each sort of individual thing our user is trying to accomplish, but translating goals into formal representations is, as easier than generating these things in blue. The last step that we showed on the flowchart before, right, involves taking these plans and taking these symbolic action definitions and turning them into something that we can actually execute on some sort of low-level platform. In our hypothetical, our researcher was doing this by hand, but let's talk now about how we might automate that as well. Once we have a plan, right, we don't just know what high-level actions need to be taken in order to accomplish it. We also know what the environment needs to look like at every step along the way in order to accomplish this goal, because we know what our planner expects to be true, what our planner has as the sort of preconditions and postconditions for each of these actions. And we know, for example, that after we've completed this opening the fridge action, it has to be the case that the fridge is not closed. We know after getting the wine, it has to be the case that the robot is holding the wine, and so on and so forth. And so when we're trying to build controller implementations now, we can use this as a scaffold to make whatever learning problem we need to solve to get these controllers much easier. We're going to try to learn a policy now for every one of these low-level controllers, and the reward from that policy is just going to come from satisfying the postconditions of the associated action. And so what really all of this symbolic scaffolding has led up to is a way of turning a long horizon RL problem, right? This sort of fuzzy natural language specification that's going to be associated with some final state in the environment, a way of turning that long horizon RL with sparse reward into an RL problem that has a nice, dense, well-smoothed reward that we can maybe even solve by training a bunch of sort of smaller modular policies. And here's a sort of representation, right, of what this might look like. Once we've done this, we're just going to sort of individually train maybe some little controller associated with each of these high-level actions that we previously defined. Okay, so here's another look at our sort of overall system architecture again. Our language model is going to produce some sort of high-level symbolic representation of a planning domain. A symbolic planner is going to turn that domain definition into a sequence of concrete plans for some set of plans that we're trying to solve in this environment. an RL algorithm is going to take each of those plans and try to sort of train controllers such that each of those plans is actually sort of low-level executable, using the scaffolding provided those plans as a dense reward signal. And the nice thing about this is that if any step of this process fails, we can always just back up to the previous one and ask for updates, either to our symbolic plans or to our symbolic action definitions, such that when we then try to do the forward pass, things are actually going to succeed. If you want to think about this with your probabilistic graphical models hat on, here's, I think, another way of thinking about this problem. We're going to observe some commands. We have a reward function that is eventually going to deliver to us some rewards that we get to observe. And we have to impute all of this intermediate structure if we imagine some sort of symbolic generative process that's actually giving rise to these rewards at the end. That being said, I think the procedural view rather than the sort of PGM view of this is a little bit easier to reason about. Because like intuitively, what is this going to do? It's going to propose and implement some operators, and then it's going to try to use those operators inside plans. If those are wrong, then if the operator definitions are bad, then the planning step is going to fail. We're going to find that we can't actually produce well-formed plans for all of our high-level actions. And this could either be because our symbolic action representations fail to describe the environment. And that, yeah, I guess that is in fact the thing that will cause this initial planning step to fail. Once we have those plans, we're going to try to use them to learn, and the learning step might fail. And if the learning step fails, it's because either we've like really failed to correctly formalize the environment, or just because we're asking this low-level policy to do more than it can learn on its own. We're asking it to sort of learn to do something that has a longer horizon than RL is going to work for. We're asking it basically to solve a sort of impossible exploration or inference problem that's hard to fit into some sort of fixed-size neural net or whatever. And so what we're going to wind up, if we sort of keep doing this forward thing, backing up when planning fails, or backing up to our domain definition, backing up to replanning when learning fails, or backing up to our domain definition when planning fails, is a set of a sort of library of actions that's basically tailored to the dynamics of our environment and the limitations of whatever learning algorithm we're using in the far right box to do learning at the low level. So if there's some piece of environment state that's relevant to the distribution of goals that we care about, eventually we're going to need to include that state in our action definitions in order to wind up with planning problems that it's possible to learn to solve. And if there's a planning problem that's simply too hard for our learning algorithm to solve, then this is going to have the consequence of going all the way back up and breaking our symbolic action representations into smaller pieces that give rise to simpler learning problems. And so overall, what we're going to learn basically is a symbolic world model over here that's just expressive enough to do all of the things that our low-level learning on the far right isn't able to do. Bilka, do you have a question?
Oh, yeah. So I think you answered it. Yeah, I'm sure.
Okay. In general, people should feel free to interrupt.
Yeah. So if you already answered it, then the question was so it wasn't clear how the preconditions and post-conditions are generated as a result.
Yeah, they are literally just we take a big language model and we say, I'm in an environment, here are the sort of sensors that I have access to, here are the things that I can test, the fluents that I can test or whatever. Here are maybe all the actions that I've generated so far. Generate for me a definition of open.
The language model.
The language model outputs that thing. And it doesn't know, it doesn't get to interact with the environment. It doesn't even know that this is then going to be fed into some learning procedure at the end. And so it's very probable that the first time you try to do that, it's going to be wrong. Well, I mean, just that if you think about the space of like all possible strips operators, it's gigantic, right? If I had to do explicit enumerative search in the space of all possible strips operators while doing, say, inference in this model, I'm just never going to find the one that I'm looking for. But the set of sort of plausible implementations of open or chill or whatever with respect to some set of predefined fluents, this is much smaller, and this is exactly the sort of common sense knowledge about how the environment works that we get out of these language to code models. So I think that's really the intuition, is that we're not, at the end of the day, whatever we come up with here has to be low-level executable, and we're just using the language model as like a prior over what implementations are even worth trying in the first place. Yeah.
I also had a question about this. I feel like coming up with sort of like the definitions of the operators is a pretty nuanced problem. So for example, you have like this slice operator, right?
Yeah.
And like part of it was like a precondition, like the object has to be on the table. Like, okay, what if I also want to do on a countertop or I want to do on a cutting board?
Yeah.
And I feel like it's like a really hard like systems design question to actually build systems or like to have a like to expect a language model to build like a system with like really nice interactions. Like should the thing that I'm cutting on, should that be like an argument or something like that? Or should it be preconditioned? But I feel like it's just like sort of I feel like there's a lot of nuance.
Yeah, I mean, we'll look at some examples that get generated in the end. I think, you know, again, well, so two comments there. First, one thing that we're really assuming here that's quite a strong assumption is that we have access like to a type system and a set of predicates, and that those are predefined and not part of what needs to be learned. And those already go a decently long way towards constraining the kinds of operators you're able to implement. I can talk more, you know, I think it is possible in principle to learn those things as well, and can talk about how we think about possibly doing that in the future, but that's thing number one. And then thing number two, again, is that, you know, maybe the high level message here is that there's many ways of implementing each of these things. And some of them are probably like annoying or counterintuitive to a human programmer, but are just fine from the perspective of scaffolding learning and having planning like not fail and produce feasible plans. And that's really the only criteria we have here. Yeah.
Part of the other thing that's very closely related to the gap is the fact that something like a chair is not geometric fit. It's something you can sit on. And that's something you do with, it's sort of stored in memory of what it feels like to sit on a chair. So again, an appropriate rock to be used in a chair.
Yeah, I think that's all true. And, you know, again, like, I think that's exactly the kind of, you know, here, you know, the set of affordances even that like a chair makes available is exactly the kind of background knowledge that we're getting out of pre-training, right? That once you have a sort of library of predicates in terms of which all of your actions are going to be defined, like knowing the set of predicates that are associated with sitting on a chair or with using a knife or whatever, like those are the things that we want, you know, sort of human cultural knowledge about in order to inform the design of these actions. And that's what we're getting from pre-training. Okay, in the interest of time, I'm going to move along a little bit, but can do more questions at the end. I will say for, you know, this first thing that we're talking about here, this is basically the loop, right? So we have our action representations, we generate some plans, we refine them if planning fails. Once we have some plan, or once we can generate all of our plans, we try to do learning. If learning fails, we back all the way up here to the actions that were involved in failed plans, and we resample those actions and try again. How well does this work? I'm going to be presenting results here on two different data sets. This Alfred environment that we've been using as a running example, and a mini Minecraft environment that Jiayuan defined on her own. For those of you who have worked with Alfred before, this is not the sort of normal condition under which people evaluate. We have natural language, we have a like, you know, sort of black box success reward condition, but no demonstrations at all. Okay, and so, you know, to the question about are these models good at coming up with sort of reasonable nuanced operators? I think the answer is yes, or at least like, you know, surprisingly and to a greater extent than I would have expected. On the left is something that we've learned in this crafter domain, which, you know, was made up for purposes of this project and has some weird environment dynamics, like the only way to build a, you know, pillow with feathers or something is to like use a sword on a chicken, things that I think you wouldn't expect to be necessarily just like memorized inside these models. Nevertheless, you get, you know, sort of reasonable, like pretty well articulated operators. In this environment, in an Alfred, we basically recover some large part of actually the human generated PDDL definition for this domain with a couple of different decisions about how to break up some individual operators into pieces. Here's an example of the system in action. Like I said, this is a sort of silly simulation environment, so don't read too much into it, but it slices a tomato, washes a tomato and then slices it or something. In terms of sort of numerical results, basically the high-level takeaway here is this is good. You might worry quite reasonably that the big language model that we're using here has already seen Alfred, and this is sort of the function of the mini Minecraft environment, which was definitely never seen in training. Have rules that are a little different from normal Minecraft, and models still do quite well on their own. I guess the maybe cool and most exciting thing here, sort of going back to our previous claim about generalization, is that there was no change to the underlying code base when we moved from Alfred to mini Minecraft. There was not even really any kind of code development of these things. People were talking, but I don't think Jiayuan saw the code base that we were using to do any of the planning stuff until these experiments were run. Cool. So what did we learn here? And I think the main thing one of the main things that we learned is that planning is still hard for language models and things that look like language models. But writing formal definitions of planning problems is not hard. And so we can take models that have been trained on a bunch of code, use them to generate symbolic representations sort of on the fly, and then use those symbolic representations to solve the problems that we actually care about solving. And even when it's sort of hard to do the formal computation associated with a planning problem internally for one of these models, they can sort of automatically externalize it and use nice, robust existing tools that we have for doing formal reasoning generally. And what we get out then is a system that, at least in these sort of relatively simple kinds of problems, exhibits the sort of ML-like scaling and symbolic-like generalization that we were aiming at in the motivation section for this talk. Okay, in the time left, I want to zoom out even more and talk about generalization to other problem domains. This is work led by Gabe Grand with a bunch of other people, many of whom are in this room right now. So the high-level question now is what this story might look like in domains outside of planning. And if we think very abstractly about what it was that we were doing in this first section of the talk, we might describe it as something like this. I have a language model that's generating a library of reusable code fragments. Here are these symbolic action definitions. And then a search procedure that's trying to take all of those little symbolic code fragments that we wrote and put them together to build some kind of program that passes some kind of test. Sort of before the code fragments were these abstract actions that we defined. The search procedure was a planner that was trying to build from these a plan. And the validation procedure was basically whether the plans that we produced provided enough scaffolding for us to learn to solve these problems at the low level. So to say this another way, right, this is our validation procedure. And in this framing, we can think of what we were doing in the first half of the talk as an instance of a much more general class of what we can generally refer to as program synthesis problems. And these kinds of problems show up in all sorts of other places. In inverse graphics, right, we might want to go from an image of a chair to a symbolic description of the chair, maybe in the form of a program that, when executed, renders the chair. And we might want to do this by learning a graphics library that knows how to render individual pieces of this chair and that can be composed together to build different chairs of different kinds. We mentioned theorem proving at the very beginning of this talk as another application. We can also sort of cast this as a program synthesis problem where I want to build up some library of useful lemmas or intermediate steps or proof strategies such that it is easy for me to search for a proof of any theorem that I'm interested in proving. Traditional sort of PL approaches to these program synthesis problems look a lot like, and you can think of as sort of general versions of classical planning. So a human goes out and engineers some domain-specific language with the right set of high-level functions for the problems we're interested in. Humans also engineer maybe some kind of search algorithm that sort of has the right heuristic for composing these things together in service of a goal. And this kind of search can be very, very powerful, even if deployed in a sort of very stupid way, right? It can solve inference problems really quickly and search problems really quickly that are hard to do with an LM just because it's like super cheap to run search and easy to sort of enumerate and backtrack. Now, there's been a recent interest in sort of library learning approaches that try to solve not just one search problem using a human sort of pre-human written domain-specific library, but then instead start with a collection of related search problems and try to figure out what the library is that would allow you to solve all of those search problems jointly, simultaneously. And, sort of at a high level, the way these methods work is alternating between search to find programs and compression, which takes a bunch of programs that have been found, extracts reusable pieces from them, and then adds them back into the base library that's being used for search. But even these sort of library learning methods, which are kind of the state of the art in program synthesis right now, run into problems that they can't solve. And maybe unsurprisingly, they're mostly problems that involve squishy background knowledge of the kind that you learn from other people and not from thinking about program synthesis problems. So as an example, name that function f that passes this test. It filters out vowels. Okay. But it's very interesting that everybody says that this filters out vowels, right? Because the letter U doesn't appear in any of these functions at all. And if you just wanted a program that passed all of these tests, you could do just as well with something that filters out, A, E, I, and O. And I guess Y is supposed to be on that list and is not there. And so there's sort of two things to notice here, right? One is that this is just a hard search problem, and generating this sort of arbitrary sequence of characters is going to require you to go quite deep in the search tree and might take a long time. Another thing is that when you try to solve this problem, you bring to bear, again, like common sense knowledge that comes from your knowledge of English orthography and not from your knowledge of how this particular problem or how to solve this particular problem. But this is probably what the sort of programmer intended here and is probably going to be necessary to get a program that generalizes in the right way. So how can we build a system that can solve these kinds of problems as well? And I think what this example suggests is that in the same way language models provided a sort of useful prior over high-level planning abstractions, they might also provide a useful prior over the kinds of reusable program fragments that are likely to be helpful for symbolic program search. So as in kind of the first piece of this talk, we're going to solve these problems by prompting language models with descriptions of the search problems that we're trying to solve, and then ask them not quite to solve those problems, but to produce a library of useful reusable functions that would be helpful for a symbolic search procedure that's then going to try to solve them. This is actually not quite right as a description of what we actually did in this paper. The way you get these reusable functions is not just by asking language models to sort of write the functions, but by asking them to try to solve the programs, pulling out the reusable pieces, and then putting those into the library that symbolic search uses. But I think the high-level intuition is really the same. Good, and and then we have a loop that looks quite similar to the loop in the first half of the talk. We have a language model giving us a prior over code that's likely to be reusable. We have a symbolic search plus validation procedure that's then verifying the pieces of code that we're producing. Maybe somewhat surprisingly, sort of key to doing this well and getting good reusable code is keeping language a part of this process by asking the language model to write down code that has human readable function names and human readable documentation comments. And without that, it can't actually figure out how to compose these library functions into even larger abstractions because it can't reason about the behavior of the code that it itself wrote. Cool. So in terms of sort of what the evaluation story looks like, standard program synthesis benchmarks and sort of regular expression domain like this vowel thing that we looked at before, some reasoning that's not actually about images, but about sort of relational graphs, and then some real graphics programs at the end. Excuse me. And as before, I think the interesting thing here is that we write meaningful reusable functions and that we discover meaningful reusable functions with human readable names and human readable descriptions just from interaction with the environment and a language model proposing what these abstractions are. So we get a polygon drawer, we get a thing that scales things up to different sizes, we get a sort of generator of things with radial symmetry and a staircase and all that. Sometimes the language is wrong, and often when the language starts out wrong, then the sort of language about subsequent functions that use an initially wrongly documented function get even worse. But when things sort of stay on track, then you really do get kind of nice, reusable, composable abstractions. Good. I flashed this on a previous slide, but we do actually get this vowel function that we were looking at before, which in fact on this little regular expression domain, no previous program synthesis method has actually been able to get exactly right, and functions that do some other non-trivial string manipulation. Lines go up on these benchmarks. Okay, so what did we learn here? I think maybe the high level takeaway is that symbolic and neural search are complementary, but you need some way for them to talk to each other. And natural language actually provides a pretty useful bridge for that. So by getting language models to document symbolically synthesized code, or code that's been sort of generated by a language model, symbolically compressed, and then needs to be renamed, you get better generalization than either kind of pure neural or pure symbolic program synthesis methods on their own. And again, sort of in keeping with the theme of the first section, I think this is really about learning world models, learning reusable abstractions that are tailored to the limitations of some downstream inference procedure. We're going to learn the reusable high-level fragments that are precisely those that our symbolic search procedure in this case wasn't able to reconstruct on its own. Okay, it's 4:50, but I really want to talk very quickly about this last bit. Also, the name has changed. Also, this is now on archive. It is called deductive closure training, and I'm going to try to talk about it in like 60 to 120 seconds. What are the implications of sort of classical formal reasoning techniques for training language models themselves? We talk a lot about problems with hallucination, especially in modern language models, right? Prompts that, if you prompt them to do tasks, you get outputs that are wrong, that are sort of internally inconsistent, that contradict themselves or contradict facts that are actually true in the world. And it's important to note that this happens in all of the LM applications that I've been describing today. We get bad sort of action descriptions. We get bad symbolic libraries. We get bad comments on those libraries. And for these applications that we've been looking at, this is a little less of a concern than sort of normal applications of language models because we have the symbolic validation step at the end as a sort of outside source of ground truth. Right, if our model writes bad code, we can discover that and just throw away the code. Can we use related ideas to get better supervision for language generating systems themselves? And the sort of key idea here is even though these language models are generating free-form language as output, many of the properties that we would like LMs to satisfy have like nice formal descriptions. And one that we're really going to focus on here is coherence, right? If the model asserts P, then it should not also assign high probability to not P. It should not also assign high probability to things that contradict P. And the cool thing is that one thing that models are really good at is labeling logical entailment relations between statements. This is a sort of classic NLP evaluation task. We have good benchmarks and leaderboards, and today's models are quite good at recognizing whether a pair of sentences are contradictory, even if it doesn't know which one of them is right. And what this suggests is a very simple off-the-shelf way of taking a language model and improving its coherence. Just ask it to like generate a bunch of statements, maybe that are all sort of logically related to each other, assign them all probabilities, and then find the subset of those that are both sort of maximal probability and internally consistent. And then just fine tune the model, only on those statements. And what we've done is sort of automatically generated supervision without needing any kind of external tool that will encourage the model to be internally consistent. And the cool thing, and then you just like feed that back into the language model. It makes models much more truthful on a bunch of different data sets. You can use it both for just sort of like unsupervised making things better and supervised editing if there's some fact that you want to change and have the sort of logical consequences of that fact propagate everywhere downstream. And I didn't say the student who was leading this project is Faiza Hirek, who may not be in this room anymore. Hi. Good. Okay, so big wrap up from this talk. I think maybe the high level takeaway is that symbolic methods aren't dead, and I think it's increasingly clear that for a lot of the reasoning problems that people, especially in LLM land, worry about these days, you can't do those efficiently or precisely or sort of verifiably inside a transformer, no matter how big you make it. But for exactly this class of problems, we have really good classical search methods. And it's pretty easy to get a model to actually write the input that you need to these classical search methods. And so the takeaway there, I think, is that symbolic models, as great as they are, maybe aren't meant to be written by humans, and that they're most useful when we think of them as being kind of cheap and disposable. And once we understand how to build them automatically, and we've seen only very simple examples of this in this talk. But if we had like really good, really general purpose tools for doing this in other problem domains, I think this opens up a sort of big space of nice kind of neurosymbolic methods that really leverage all of the work that's been done on symbolic reasoning and, sort of methods that you can scale up with more computation that give you formal guarantees of correctness that we can't get with today's models. And I will wrap up there. Thanks to everyone who did the actual work that I was talking about today. Yeah.
Hey, great talk. If you don't, are you able to go back to the main graph?
I am.
Go with the whole, okay, great, thank you.
Theory.
Just a couple of questions related to the structure on that slide.
This guy.
Further back. It's the whole graph just showing the process of
Oh, yeah.
planning with it. Yeah, exactly, right here. So a couple of questions here. The refinement step, like checking the planning fails, is obviously the important part here. I'm guessing in this system, you're sort of running through sim and seeing if you're either succeeding or failing.
Yeah.
So obviously, one of the curiosities here is, okay, you have like a trainable model here that is able to check plans. Like if you're expanding this to a real world system,
Yeah.
It succeeds or fails, sort of like a GAN style training for planning. And I'm curious from your perspective, if you think either A, this is a feasible approach that maybe just needs more data or scaling or something like that, or if there's something fundamentally different in the plan generation space than in this case image generation that would make this approach not work super well.
So to make sure I understand, the question is, can you replace like doing real rollouts in the real world in that last step with
replacing the checking, planning, failing, and the iterative process with a concurrently trained learner?
Yeah. Maybe. I mean, being like truly not a robotics person, I would be hesitant to be too confident that that would work at the low level, just because so much about like contact is hard, like kinematics is hard. And if you look at even the best like video generation models that we have right now, right, the physics is not great. And so I would be a little skeptical that you can verify, that you have like, in a really general way, that it's possible to validate the correctness of a low-level controller, train that low-level controller entirely in sim, without some amount of going out to the real world.
Okay.
For Alfred, probably you can do just fine. But I think probably in the real world, and one thing to sort of remark here is that I've been talking about the thing that lives in that black box as RL. It doesn't have to be RL, right? It can be classical motion planning, where you just say, okay, here's the sort of short-term goal that I want you to accomplish. See if you can plan your way in some high-dimensional configuration space there with like RRT or something. And I think you could just like drop that in and it would have the same properties. In fact, what we're really doing in there is something pretty, or that's kind of in an intermediate where we do try a bunch of random trajectories. We see if any of them succeeds. And then if we do, we use that as supervision for the low-level controller for the next time. Yeah.
Quick question about parsimonious. Is that something that you impose explicitly on the plan of the program, or is it kind of implicit from the feedback?
That's a great question. So here, there isn't really any kind of formal parsimony constraint. I think we do, if I remember right, some amount of filtering out of action definitions that look like they're trying to accomplish the same thing. We see if we can get away with just one or the other. But there isn't any sort of explicit optimization here for like find the smallest set of actions you can get away with. Over here, yeah, I guess this is the place to do it. When we are sort of pulling out these libraries of reusable functions, there is an explicit parsimony constraint that we're actually using this method called Stitch that was developed by some folks from Armando's group here, including Batty and various others. That's like explicitly trying to find the set of functions, the smallest set of functions, basically minimize some description length compression criterion. Yeah. And I think it's an interesting question, what the right way of, better getting a parsimony constraint in here is.
Well, there are two questions.
Okay, maybe do those and then Theo. Henry says, could this approach do better with chain of thought prompting if we ask it to take smaller steps in the plan?
For a second.
For Lilo. Is there some chain of thought somewhere in the loop? Gabe can answer this better than me.
So we tried that type of thing for proposing abstractions. I think largely due to the choice of BSL, like, so in Lilo, we're working with these really traditional method calculus representation. And just language models struggle with that, but I think like in something like Python, yeah, sure.
Yeah. So Henry, if you didn't get that because it wasn't in the mic, here it didn't make much of a difference because the programming languages are weird and the model's like not actually all that great at writing them, but for more common languages, maybe. Okay. Evan says on slide 41, there is a series of things that say backtrack if the lower level algorithm fails. How do you decide if you should keep pushing the lower level algorithm, giving it more time, or decide when to back up? Yeah, and so the way we're doing it here is there's just a timeout at the low level, and basically what we mean by the low level thing failing is that it fails to learn or fails to like hit the right post conditions within some number of seconds that I can't remember off the top of my head. But in general, right, this is sort of the nature of latent variable models, right? You have two coupled latent variables. You're having a hard time finding a configuration that's congruent. Should you do more search on one side and then sample the other side or vice versa? You can kind of think of what we're doing here as just something that looks like Gibbs sampling that doesn't have like a particular preference for picking one side or picking the other. If you had a user in the loop, how could a human help? Great question. So I think the places to hook in here are one, just asking for high level validation of each of these. Like, does this look like the right operator? Does this look like the right plan? What things am I missing every time you're doing one of those resampling steps? And I suspect like you could get pretty good feedback that way that would be much less work for a person to provide than writing all of these things out by hand. Okay, Theo.
Yeah, my question actually is pretty similar to your first question. Maybe that's it as well. But if you give a user system like this, pretty quickly the user is going to ask you to do things that the robot can't actually do.
Yeah.
So like, have you thought about whether you could imbue these systems with some sense of what actions are even possible using the language model together with some sensory information, or do you think like, because like ultimately you could try and replan over and over again.
Yeah.
But do you think that's the most desirable way to handle that, or?
Well, okay, right. So there's two reasons that something might be impossible, right? One is that just like with respect to the sort of building blocks from which you're constructing your formal representation, there's no way to accomplish some particular high level goal. And maybe there's one way for things to be impossible here, but right, like or I guess just like the laws of physics don't allow you to do it. Yeah, but that at least is like recoverable from in the sense that you can go back and you can change your action definitions to eventually get there. So, I think you can imagine having a top-down constraint that says like the user or, some sort of common sense model that's sitting there at the top level saying the user has asked me to do something impossible to like unfry their egg. And I know there's no way I can define any sequence of operators that I can chain together that will satisfy that. And then there's the like, okay, with respect to the set of things that I have tried to do, maybe there's also like a useful training test distinction here in the sense that like, if I've done this and it's a little slow and I've fixed my library and I put this system out in the world and then a user says, oh, I want you to like, I don't know, make me a BLT and I haven't actually like learned to slice bread yet, you should be able to say, okay, I could in principle learn to do this in this environment, but with respect to the set of operators that I've defined right now, I don't expect there to be any plan that accomplishes that goal. And I think that's probably the right thing to do.
If there are any questions on the tickets.
I can stick around for a couple of minutes if that's okay with you. Good.